Hello, everyone, and welcome to yet another meetup of Data Science SG. Just a little bit of background for those of you who might not know. Data Science SG was founded in 2014. It has over 9,000 members on meetup.com and is one of Southeast Asia's largest data science groups. Really, we all just gather together to talk about data science industry use cases and applications. And today we're very excited to have and partner with AWS and a great speaker, Suman Devnath, who is a developer advocate there. I'll let him introduce himself, but I just want to reiterate that this is a space for learning and the sharing of resources. So in the future, if you're interested in sharing a talk or pointing us in the direction of a potential speaker, feel free to reach out. And over to you, Suman.
Yeah, sure. Thanks so much, Swanima, and thank you so much, the whole community of data science in Singapore. So glad to be here. And what we are going to do today is we are going to talk about one of the cutting edge networking model or architecture or the algorithm, whatever we call it, in the field of not only in the field of natural language processing, but as this is predominantly being used these days in computer vision problems as well, and that is transformers and BERT. And my personal intention is to give everyone an intuition of what these networks are and how it actually works under the hood, and connect with people and learn from everyone. And I would request everyone to connect with me at later point in time, after this session, and share their learning, and we can build something together in the days to come.
Thanks so much. And over to you fully now, Suman.
Sure, thank you so much. So let me first share my screen. All right, so I hope my screen is visible. So what we are going to do now is we are going to go over some of the theory about transformers before we get into the actual demo. Okay, so for me, when I started learning about transformers, what I felt was it is quite an advanced topic in the sense if you're new to deep learning. But the more I read about that, I realized that it's not that difficult, right? So, and the coding part is the easiest part if I really have to put it in that context. So what we are going to do is for next 30 minutes or so is we will try to understand what transformer is and how it how it is used in BERT. Okay, and at later point in time, if time permits, we will go over a quick demo on SageMaker. But in case we don't get time and we really don't want to rush, we may split that to into another meetup maybe in the next month. Okay, but feel free to ask questions whenever you have any. And before we start, I want to share one small thing is, we are going to have some quiz in the middle or towards the end, and feel free to participate. I'm going to give away a few AWS credits, and not only that, I'm going to share one ebook with few of you. I have a licensed copy of that, and that is the book, one of the best book that I have read, and I've been reading on BERT. So I'll strongly recommend that as well. So I'm going to share that towards the end. Okay, so feel free to participate and ask questions as and when you get it. Okay, so with that, let's get started. So if you think about natural language processing as an overall field, what it is actually is it's a subfield of linguistic and computer science, right? So if you think about it, as I'm speaking English, or maybe if I speak my mother tongue, Bengali or Hindi or whatever, these languages are very, very easy to understand for the other person, provided that he or she knows that language, right? And if you think intuitively, these are very complex language, right? So we human can understand, but it's very, very difficult for a computer to understand these languages. right? So whether it's English or Mandarin or French or whatever, right? So the idea of NLP is to build a mathematical model so that the computer can understand these kind of languages, right? And what are the use cases? The use cases are many, right? So you can think about text classification or speech recognition. I'm very sure you might be using devices like Alexa, and you might be using maybe auto-generated text in your mobile phone, and so on and so forth, right? So all of these are actually different use cases of NLP. Okay, so now the whole idea about NLP is to build that mathematical representation of all these languages, right? So if we can program our computer in a way that it can understand the language in a in a more mathematical way, then our problem is solved, right? So that is the whole idea about NLP. Now, this is where different algorithms comes into picture. So if you start from 2013 or late 2000, early 2000, we had various different algorithms like word2vec, Glow, fastx, and so on and so forth. And all of these algorithms, they used to do fundamentally the same thing. What it used to do, it used to represent a word in the form of a vector. Okay, because at the end of the day, computer understands only numbers, right? So the only way that we can represent a sentence or any message is in the form of numbers, right? So that's what all these algorithms used to do. And what happened is, in last couple of years, especially in 2017, a new paper came in called Transformer, and the name of the paper is "Attention is All You Need," and that has changed the whole paradigm of NLP in the data science world. And if you see you can search it in the internet later on, you will find that from 2017, there is a lot of research, a lot of products has been developed, and a lot of investment companies have been doing on NLP because of the ease of use, or the ease of solving very, very complex problem using these models called transformers. Okay, and later on in 2018, we got another model which is kind of an extension, not an extension. We would see how BERT and transformers are related, but it's kind of you can think of BERT as a special type of transformer, if you just have to define it that way. Okay, so at its core, we are going to spend today, most of our time to learn transformer. But at its core, what transformer does is it tries to understand the contextual meaning of a sentence. Okay, so we will try to learn what is that contextual meaning is. But I want you to do an experiment at later point in time, maybe after this session, not now, because I'm very sure you all have mobile phone in your hand, or maybe in your room, wherever you are now. Try this out. Okay, take your mobile phone and open a text, maybe a notepad, or maybe WhatsApp or an SMS or whatever. Just open that message and type something, and make sure that you just type the first word. Okay, so let's say you want to say to your friend that I am coming to your home. Okay, so just type I, and then you will see that it will you will see that in your whether you are using iPhone or Android, whatever it is, you will see that it will predict the next word. Okay, so now don't type anything, just type I, and then keep on selecting the word that it is suggesting, the right word it is suggesting. Okay, it might suggest 2 or 3 words. Just keep on clicking on that, and you will realize that when that sentence is having 3 or 4 words or 5 words, the sentence will make some sense, right? But beyond that, if you keep on clicking on the next suggested word one by one, one after another, you will see that as the sentence grows, it will not make any sense, right? And that was the exact problem the previous generation algorithms around NLP, which are things like RNN or LSTM had, where if we have to do any, let's say, any translation work or any kind of NLP based task, uh, it it never used to read the whole sentence at a time. It used to read word by word. So basically it used to process sequentially, one word at a time, right? And that's where the problem used to start, that since it was processing word by word, as the sentence length increases, it used to forget what it has learned in the initial part of the sentence. Okay, and this is one of the problem which transformers solve. So now, enough about the history and all of that. So let's get into what transformer is. So what we are going to do is we will take an example and then we will learn about transformer. So transformer can do a lot of NLP based tasks. So for this example, we will take a language translation task. Okay, and then we will learn how transformer solve that. And during this process, we will come to know about internals of transformers. So let's say I have a sentence called "I am good." Okay, and we want to convert it into, let's say, French. Now, what transformer has is it has two different blocks. One is the encoder block, as you can see here, and one is the decoder block. Okay, and the whole objective of the encoder block is to make a better representation of this sentence "I am good." Okay, so now if you remember, just a while back we learned that we had a lot of different algorithms like word to vec, glove, and so on, which can represent a word into a vector. So we can argue that I can convert this sentence "I am good" into a set of vectors, maybe 3 vectors, because we have 3 words, so 3 vectors, and that's it, right? So all those algorithms never used to capture the contextual meaning of the words. Okay, and that is what this transformers encoder block will do. Okay, so how it does, we are going to see that next. But the idea is this encoder will take this sentence "I am good" and it will make a better representation of this whole sentence. Okay, and what I mean by better representation is it will have the representation of "I am good" will have a contextual meaning. That means if this is the sentence "I am good," here, as we know English, we know that this "good" is referring to I, right? So all those information will be embedded in the representation. So now let's go deep and see what is inside this encoder. Now, if you look at this encoder, I have just shown a block diagram of this. The way that transformer works is it has multiple encoder layers. So you can see that encoder layer 1, encoder layer 2, encoder layer 3, and so on and so forth. Right? So you can have multiple layers. I guess in the original paper of transformer, the number of layers that they have used is, I guess, 6 or 9. If I do not remember the exact name. The number, but you get the idea, right? So you can have any number of encoder layers within your whole encoder block. Okay, and all these layers are identical to each other. And all it does is it takes the input. So the first layer takes the input sentence and it sends the output to the next layer. Okay, and so on and so forth. And finally, at the end of the nth layer, you get the better representation of the sentence, which you will pass it on to the decoder block, which we will see at later point in time. But now the question remains, what is there inside these encoder layers? So as we just discussed, all these layers are identical. So we can just open up one of the layer and see what is there inside. Now, if you see inside the encoder layer, we have 2 blocks. One is multi-head attention and another is a feed-forward neural network. So feed-forward neural network is a standard, a fully connected neural network. So nothing fancy about this. But this is where things get interesting. Okay, so we have something called multi-head attention. Now you may ask, what is this multi-head attention? So now before we get into what is multi-head attention, we have to first learn what is self-attention. Okay, and this is the core of transformer. If you learn this, if you understand this, I think half of the task is over. How transformer works. Now, if you take this sentence, a dog ate the food because it was hungry, right? So if you look at this sentence, you can say that, as we know English, we know that here the word "it" actually represents or refers to the dog, not to the food, right? And that's why if you see in the right hand side, the representation of "it," right? It will have the embeddings with all the information, but if you see that, it will have a more bias towards this word dog, and that's why there is a thick line. Okay, so this is what a self-attention actually means. It means that when you represent every word, you have to make sure that that word contains the embedding which highlights the dependency or the relationship of other words in the sentence. So the idea is, if you take this word, let's say dog, right? So when you represent dog in the form of a vector, make sure that vector have all the information of the relevance of that word in the whole sentence. Okay, so in this example, if you see, it relates to dog, or it is referring to the dog. That's why this line is thicker, right? So now we have to come up with an algorithm which can do this, right? So the next question is how we can do that. So now let's take an example. So the example that we are going to take is a small one, so that we can comprehend it well. So let's say I have a sentence called "I am good." Okay. Now what we do here is, before we get started, just remember that the task is we have to make a better representation of this sentence "I am good." Okay, that is the final ultimate task. Okay, and we are at the first step now. Okay, so what we are going to do is, we will, let's say this is our sentence "I am good," and I have created a matrix which is nothing but a vector representation of all of these words, right? So you can use any technique to convert this each and every individual words into a vector. So if you see, the first row, that is x1, is a representation of this word "I," and then "am" is the second row, and "good" is the third row. Okay, and if you see here, the size of the matrix is 3 by 512. That means each word is represented in a vector of 512 numbers, right? So this first row is having 512 numbers, second row is also having 512 numbers, and so on. Okay, so now this is our input matrix X. Okay. So what we do next, we are going to create 3 different matrices from this input matrix. Okay, we don't know why we are creating this, but just assume that we are going to create 3 different matrices, and we will call it as query matrix, key matrix, and value matrix. Now how we can create this? This is our input matrix, as we have just seen. What we will do is, we will create a query matrix Q, we will create another matrix called key matrix K, and we will create another matrix called value matrix V. Okay, now how we are going to create this? We are going to create this using a weight matrix called WQ, WK, and WV. Now what are these matrices? These are the matrices which will be trained during the training process. Okay, and what we do is, we simply multiply these weight matrices with the input matrix. That's all. Okay, so you can think of these are randomly initialized metrics, and all we do is we multiply this with the input matrix. Okay, so now if you see here, the size of this matrix is 3 by 512. And why it is 512? Because we have used an embedding of 512 length, right? And why this is 3? Because in this sentence we have 3 words. Now, these query matrices or key matrices and value matrices all have or vector length of 64. Okay, so if you see here, the first row represents the query, key, and value vector of the word I. Okay, so now I have one question for you. Okay, so let me just take the pen. So if you see here, the dimension of this matrix is 3 by 512. And the dimension of all of these is 3 by 64. Okay, and this is also 3 by 64. Sorry, 64. So now, can anyone tell me what should be the dimension of this WQ? Any one of you, can you tell that I am multiplying the input matrix as 3 by 64, okay, and I'm getting a 3 by 64 matrix. What should be the dimension of this WQ or WK or WV? All would be same, but can you just guess? Exactly. Absolutely right, Nitya. So it is of 512 by 64. Okay, so what we are essentially doing is we are creating 3 different random matrices, and all of these are random, right? So it can have garbage numbers. Initialization is completely random. But what we are essentially doing at the end is we are creating this query matrix, key matrix, and value matrix. And all of that is ultimately creating 3 different vectors. One is query vector, key vector, and the value vector for each and every word. And the size of this is 64. So remember that 64, because we are going to come back to this in some time. So a great answer, Nitya. So next is what, right? We started with X metrics, right? And now we have 3 more metrics, Q, K, and value metrics. So what we are going to do now, right? So this is where the transformer comes into picture. So this whole process is a 4-step process, okay? And the first process is we are going to do a dot product between query matrix Q and the matrix K, which we have created. Okay, we are just simply doing a dot product. And why we are doing a dot product? If you see, when you have 2 vectors, right? Let's say you have one vector, you have another vector. When you do a dot product between that, this is the basics of machine learning. We have cos theta between that, right? So the dot product between 2 vectors shows how similar those 2 vectors are, right? So now if you see this, the dot product of these 2 vectors, these 2 matrices gives us this particular matrix. And now if you see this number, if you just focus on the first row, you will see that the first number is 110, the second number is 90, and the third number is 80. And it is quite evident, right? Because 110 represents how much I depends on I. Obviously, I depends on I the most, right? So that's why the number is the max here, right? Similarly, if you see am, I is related to am little bit more than how much I relates to good, right? So if you remember, our initial problem that we are trying to solve is to make a better representation. So we are going closer to this, right? Because this is what we want. We want to represent each and every word in such a way that representation contains a contextual meaning. So if you look at this vector, right, we can say that it's not only a random set of numbers, but it actually represents some relationship of that particular word with respect to other words in this sentence, right? In this case, representation of I represents how much I depends on I itself, how much I depends on am, and how much I depends on good. Okay, so that's the first step. What is the second step? The second step is very simple. We just divide this output. So whatever we get here, right, whatever we are getting here, we are just dividing it with the square root of the dimension of the vector. Okay, so what is the if you remember, we have used the vector size of 64, right, in the previous slide, if you have remember. So we are just divide it by the square root of 64, and this we do because of getting a stable gradient. Okay, so this is what we are doing in the second step. Now the third step is we just take the softmax of that. Okay, and why we are doing this? Because we want this to be within a decent range, so that it doesn't get blasted to a high number or a small number, right? So we are just squeezing it down using a softmax. So now if you see each row, which is a representation of each word, if you sum them all, you will get 1, right? Which is a standard definition of softmax. Okay, so the first step is dot product. Second step is doing a division with the dimension of the key vector, and the third is normalization using softmax function. Okay, now the final step is the final step is attention. Okay, and if you look at this before we go there, if you look at this first row, now it's very evident, right? If you see the representation of I, it's 0.9, 0.7, and 0.3, and that translates to this, right? So I is related to itself by 90%, 7% by am, and 3% by good, right? So we are reaching our ultimate goal, which is nothing but a better representation of words or in a sentence. So the final step is called attention, to develop a attention matrix. Okay, so if I go back, if you remember here, we have created 3 matrices, right? One is the query matrix, one is the value matrix, and another is the key matrix, right? And in this 3 steps, we have used the query matrix and the key matrix, but we have never used the value matrix, right? And this is what we are going to use in the 4th step. Okay, so in the 4th step, what we do is we just multiply the resultant of step 3, which is nothing but the softmax of this particular matrix, right? What we got in the step 3, we just multiply that with the value matrix. And this is not a dot product, okay? And the way that we do the multiplication is like this. It is kind of a weighted sum of vectors, okay? So let's say I have to represent I, right? So what I will do is I will multiply 0.9, okay, with the whole vector of I. Okay, so this is the value vector for I, right? So I'm just going to multiply 0.9 with this vector, okay, and that is what I'm doing here. Then I sum it, I add with 0.7 with the vector which represents am, okay, which is here, and similarly for good. And at the end, I get Z1. Okay, so similarly, I will get Z2, I will get Z3. Okay, and if I just keep all of them, then I will get a matrix called Z, and this is nothing but is called attention matrix. Okay, that's all that transformer encoder block does. Okay, for this particular self attention step. Okay, now you may ask that if you have a sentence like this, a dog ate the food because it was hungry. So in this case, you would know that I know that it represents dog here, but this it is little ambiguous because you might, computer might think that it might be referring to food, right? So it is, we understand because we know English, but the computer may not understand that. And that is where what we do is we don't create only single attention matrix Z. We create multiple attention metrics like Z1, Z2, Z3, and so on, right? So in this example, we have 8 matrices, right? So similarly, whatever process that we have seen, we will do 8 times, okay, and all at the same time, and then we will just concatenate. And this is what is called as multi-head attention. And the reason that we do this is because if we just go ahead with the one representation, it might happen that this representation will have a bias towards, let's say, only food, right? But we don't want that, right? We want that the computer to learn in a much better way, and it should not be biased with just one attention, right? And that's why we create multiple attentions, and then we just concatenate all of them. Okay, and this is what multi-head attention is about. So if you think about it before we proceed, we have taken the whole sentence, right? If you remember here, if I just go back a little bit, we have taken the whole sentence at a time, right? We have taken this whole sentence at a time, and we have computed all these, 4 mathematical operation to come to this attention metrics. Now, if you think about it, we are not sharing the position of each and every word, right? Because transformer doesn't know which position a particular word is coming, right? And this is where positional encoding comes into picture, right? So in the previous generation of NLP-based models, it used to process each word at a time. So whenever it is processing the second word, it knows that this is second word because it has processed one word in the past, right? But when you give 10 words at a time, it doesn't have any information which word is the 10th word, which words is the 9th word, and so on and so forth, right? So it's just like this. Let's say I am about to host a session, and the conference room is closed, and everyone is there outside in a queue. And someone just opened that door, and everyone just flushed inside this room. So at that point, I don't know who was the first person who was there outside in the queue, and who was the second person in that queue. So I have no idea about that. So let's say I want to know who was first, who was second, who was third, and all of that, right? So how would I know this? So this is where positional encoding comes into picture. So what we do is we take this input matrix, and then we just add another matrix P, and then we send this as an input. Okay, we don't send this as an input, but we just add one positional matrix, and then we send this to the transformer. Now you may ask, how we are going to generate this P matrix, right? So this is a little bit mathematically, convoluted, but I'll try to explain it in a very simple way. So imagine that we have, so in the past, we have represented every word into 512 dimension, right? So for the simplicity, let's say it's not 512, but we are representing every word in a vector size of 4, okay, in the 4 dimension. Okay, so what we can do is we can generate 4 random waves, so maybe 4 different functions, and it can be of sine function or a cosine function, as you can see here. Okay, so since I have represented every word in 4 dimension, I have 4 different waves here, or 4 different functions here, right? And in the x-axis, what we are representing is the position. Okay, and now what we will do is, let's say we want to know the position of the 30th word. Okay, so what we will do is we will just check the value of these 5 functions, okay, all these 5 functions in this particular position. Okay, and this is nothing but this particular vector. Okay, so in this case, what I'm marking now, this is for the second word, right? So imagine if this is for the 30th word, I will have a matrix, maybe let's say 30. The dimension will be more, but I will just have that whole vector which is mentioned here. Okay, so the idea is we will generate different number of functions depending on the dimension, and then we will just pick the value of all those functions, and we will just add them to the input matrix. Okay, so that's how positional encoding works. Okay, you generate a number of functions, and how many functions, it depends on the dimension of your input matrix, and then you just keep on adding the value or the magnitude of all those functions to your respective words. Okay, so this is what positional encoding is about. So now, if you just recall, where are we now? We have this input sentence, And we learned that we don't want to feed this directly to the transformer block because it doesn't have any information of the position of the words. So first thing that we do is we do something called positional encoding, and then we take that output and send it to the multi-head attention. Okay, and we have learned what is multi-head attention, which is nothing but the Z matrix, how we create that Z matrix, right? So the next thing is feed-forward neural network, right? So that's pretty straightforward. We don't want to spend time on that, but it's basically a two-layer feed-forward neural network, and with a small addition here. What transformer people did was, the researchers of transformer, what they added was they added a add and norm layer. Apart from this feed forward and multi-head attention layer, they added this add and norm layer after each and every layers. Okay, and this actually came from the idea of ResNet. If you are familiar to CNN, in ResNet also we had add and normalization, and there are many reasons why we do this. One of the reason is it takes your training a little faster and it's more stable. Okay, but if you think about it, what this add and norm does is, if you see this add and norm, if you just look at this, it has two inputs, right? One input is this, and another input is this, right? And if you see, one input is actually the output of the multi-head attention, and another input is the input of that multi-head attention. So basically, add and norm takes two inputs of the previous layer's output and previous layer's input, right? So that is what this add and norm layer does. Okay, so now if you just put it all together, it looks like this, right? So you have the input embedding. If you remember, we have used that 512 dimension embeddings, right? It can be any embedding, right? There are a lot of embeddings available. You can take any embeddings, and then you do the positional encoding, and then you pass it on to multi-head attention, then add and norm, then feed forward neural network, and again add and norm, and then that's all, right? And this goes to encoder layer 2. Now, again, in encoder layer, in encoder block 2, it will have exactly same block as this, and it will send it to encoder block 3, and so on. It will send it to, let's say, encoder block 4. And let's say you used only four blocks. Okay, so the final output of this would be nothing but a very good representation of your input sentence, I am good. Okay, so once you have that representation, what you can do is you can pass it on to the decoder, and then the decoder can then translate your sentence into some different language. So in this case, we started with a language translation problem. So maybe it can convert into Spanish or French or whatever it is. In this case, I guess it's French. So that's the whole idea about encoder. Now, we are not going to talk about decoder. Although I will share you the slide which talks about the decoder, because it will take a lot of time. And the reason that we don't want to talk about decoder is our final intent is to learn BERT, right? And in BERT, as if you remember, as I explained initially, BERT is kind of a special type of transformer. And the reason that I said that is because you can think of BERT is exactly as transformer, which doesn't have the decoder block. Okay, so the BERT has only the encoder block of transformer. That's all. And there is some special things inside that, but at its core, BERT is a special type of transformer which contains only the encoder part of transformer. That's all. Okay, so that also means there are a lot of tasks BERT cannot do, which transformer can do. Right, so we have a lot of different examples which can be solved using transformers, but not BERT. But BERT can solve very complex problem with only this encoder part. Okay, and that is what we are going to see now. Okay, so if you see next, this is what BERT is about. Okay, so bidirectional encoding representation from transformer. And why it is bidirectional? Because we are feeding this whole input sentence at a time, right? We are sending it together at one point in time. That means what? when Bert is going to read through the sentence and tries to get an embeddings of that or a better representation of that, it has the context of left hand side of the each word as well as the right hand side of this word, right? So when Bert is going to find the embedding of favorite, the letter favorite, it would know the context to the left. It would also know the context towards the right. Right, so that's why we say it as a bidirectional encoder representation from transformer. Okay, and why I am enforcing this multiple times is because this is the only thing which was not there in the previous generation of NLP based algorithms like RNN or LSTM and so on and so forth, where we used to process one word at a time. We used to process Python first, then is, then my, then favorite, and so on and so forth. Okay, so now let's see how BERT is architected. Now, the way that if you think about it, if you ask someone, let's say you ask me, right, and my mother tongue is Bengali, right? So now if you ask me that how you learned Bengali, I would say that I might have read books, a lot of books, and I have learned Bengali in my school and so on and so forth. I can keep on telling that, right? So how you can test my knowledge, right? So you can give me a sentence which is, let's say, half hidden and half exposed, and you can tell me, or you can ask me that, okay, let's say I give you this sentence, Kolkata is a beautiful, and then you stop. Okay, so if I know English, I should be able to say that, okay, the next word should be city, right? So this is what the whole intent of BERT. So what BERT did was, the researchers of BERT, which I guess it's from Google Brain, what they did was they trained they trained a model with two tasks. Okay, and these two tasks are called masked language model and next sentence prediction. Okay, and the idea that they had was, if we can train a model which can solve these two problems efficiently, that means that that model has a very good understanding of that language. Okay, and as these two problems seems like, the first problem is, given a sentence, BERT has to predict the next a missing word in the sentence, and the next problem, which is next sentence prediction problem, is that you will give two sentences, and BERT has to figure out whether the second sentence both the two sentences are come one after another or not. Okay, so let's say you give two sentences like this: Kolkata is a beautiful city, I love Kolkata. If you give this to BERT, BERT should say that whether I love Kolkata is the second sentence in this sequence or not, right? So it should be it should say yes or no, or true or false. Okay, so these are the two problems that BERT has trained. Okay, trained with. So you don't have to train it. So that's why we call a BERT as a pre-trained model. Okay, and this is what BERT has done with a large amount of data. In it has trained with the, I think, the whole Wikipedia data. Okay, and it has used these two problems to make a very good understanding of the language. Okay, it can be English or it can be any other language. Okay, so now this is how BERT works internally. So here, as we can see, we have 12 layers, and we have seen that what are there inside these layers, right? It's exactly the same that what we have learned in Transformer, right? It has multi-rate attention, feed-forward neural network, and so on and so forth. Okay, so the only thing that is different is these three embeddings. Okay, so remember that that BERT is a pre-trained model. That means BERT has been already trained for two tasks. One is this one, multi-head masked language model, and another one is next sentence prediction problem. So these two problems are the problem which BERT has been pre-trained for. Okay, and to do that, the way that the input is given to BERT is like this. First is it will have the token embeddings. Okay, so if the two sentence is this, Kolkata is a beautiful city, and I love Kolkata, what it will do is it will first put a special character or a special note called SEP. So this determines the end of every sentence. Okay, and it will also have a special token called CLS, which will show that this is the start of the sentence. Okay, so that's why we have CLS and we have SEP. And if you see, the first problem that it is going to solve is given a sentence, it should mask some word, right? And that masked word is represented by this token called mask. Okay, so these are three special tokens that BERT uses. SCP, which determined a sentence, end and other sentence start, and CLS is the token which represents the start of the sentence, and the mask, which is nothing but the word that you want to mask. Okay, so this is this is the input. Okay, so the first thing that it does is it represents that these tokens into numbers, and the second embedding that it adds is, since we have two sentences, there should be a way which will have this information that this word is part of the sentence 1 or sentence 2, right? And that is what this segment embedding is about. Okay, so if you see, all these EA segment embeddings are actually for the first sentence, that is Kolkata is a beautiful city, right? And EB is the embedding for the second sentence. Similarly, we have positional embeddings, and this we have learned. It's just exactly the same as positional embeddings that we have learned in Transformer. Okay, and once we are done with all these embeddings, we will send this data to the input layer of this encoder, and similarly it will pass it on to the second encoding layer, and so on and so forth. So in this case, we have 12 encoder layers, and at the end it will have a better representation of the whole sentence, right? It will have a better representation of the whole sentence. Now we are going to see what BERT does with this. So let's say you have this sentence, okay? Suman loves Kolkata, right? So let's say I'm trying to do a sentiment analysis of this, okay? And now I'm not in the pre-training phase. Pre-training is already done, and this is done by BERT itself. So we don't have to do that. Now what we are trying to do is we are going to take that model and we are going to just do a fine-tuning. Okay. On top of this, we are just going to do a fine-tuning for our respective problem. So the problem that we are trying to solve is, let's say, sentiment analysis. Now what we know is, when you give BERT a sentence, it will have a special token called CLS, right? So it will have a special representation of CLS, as well as it will have a representation of Suman loves Kolkata and SCP, right? It will always have that. But now what we can do is, since we know that Transformer or BERT has a contextual meaning for the whole sentence, we can confidently say that the representation of CLS contains the representation of this whole sentence, right? So what we can do on top of it is, and this is the part which is called fine tuning. Okay, this is the part which is called fine tuning. And what we can do in this fine tuning is, we can put a front end, a feed forward neural network, a single layer feed forward neural network, and a softmax function, and we can say that whether the sentiment of the sentence is positive or negative, right? So this is as simple as that. So that means none of the weights are going to change in this whole model, okay, when we do a fine tuning, because these are already pre-trained model, right? And that's what that pre-trained is about. All we are doing is we are going to add an additional layer, and we can take the output of that additional layer for our problem. So in this case, it's a sentiment analysis. That means it's a binary classification problem. So we could just take the output of this CLS token, and we can ignore all of that. Okay, so you may ask that why we are taking this. We could have taken the representation of Kolkata. Sure enough, you can always do the representation of Kolkata, or let's say Suman or whatever. But the reason that we should not take this is because if you take the representation of Kolkata, that means you are taking the representation of the third word in the sentence, right? So in that case, it might so happen at later point in time when you do the inference, you have a sentence with just two words, right? So in that case, the inference will fail because the inference will expect three words at minimum, right? And that's why if we take a CLS, we are always sure, even if the user sends one word sentence, CLS will be added by BERT itself, right? So it's always better to take the representation of CLS. Now let's take another example. In this case, let's say name entity recognition problem. Okay, so where given a sentence, it will predict each word what that word is about, whether it's a person or it's a location or whatever it is, right? So in this case, I have to read through the representation of all the words, right? So in this case, the representation of CLS is not needed for me. The representation of SEP is not needed for me, right? So all that is needed is the representation of each and every word, right? And on top of it, I can do a fine tuning, right? So just like here, I have done a fine tuning only on the CLS token. Here, I'm going to do a fine tuning with a classifier on top, and which will predict that whether a particular word is a person or a location or whatever, right? So this is the beauty of BERT. We don't have to train it from scratch. The training will be, the model will come as pre-trained using BERT, and as we have learned this, it has been pre-trained with these two tasks. Okay, and we have libraries like HuggingFace. It has a library for BERT, and it has been pre-trained with which actually is about solving these two problems on a very large corpus of data. And all we can do is we can just train our model on top of it, right? On top of it, and we can get away with that. Okay, so that's about BERT at a very high level. So if you have any question you may like to ask before we get into the demo, or maybe the demo, I still have 10 minutes. I can just go over a few of the parts of the demo, but I'll be more than happy to have another session where I can show you the demo. But if you have any questions, please let me know. So I see one question. How do you get, I think Shang has asked, how do you get all those weights? That's a very good question. So weights are something in neural network or deep learning in general is something that you learn. So you randomly initialize. So you can initialize the way that you want. Okay, so you may initialize all the weights with some random number, maybe using maybe the NumPy random function itself, and you can have the weights between 0 and 1, right? So you can have all those decimal numbers which are randomly generated, and then during the training process, just like in any deep learning network, it will have backpropagation, and it will update those weights depending on the kind of objective function that you use. So you don't have to worry about that, and that is the whole part of the training process for any NLP based model, right? So it will be trained during the training process, and all you do is to randomly initialize that. Okay, so there is one more question. 512 is equal to max length into vector. Yeah, that's correct. So 512 we have used because we have chosen that the dimension of this input matrix is 3 by 512. And why 512? Because this is the embedding that we thought that we will use for represent every word. So let's say I don't have much compute. I can represent a word with, let's say, just 64 numbers. So in that case, the size of the matrix would be 3 by 64. So it's up to us, right? But generally, we all use 512 representation, at least for this demo and for transformer. The researchers also used, I guess, 512 as the embedding length. Okay, so all right. So what I'm going to do is, I'm not going to, go over the demo because I think it would be a little more killing, I would say. But I will share the GitHub link. You can go over that, which is nothing but disaster tweet classification. That means given a tweet, it will classify whether that tweet comes under disaster tweet or not. And this is useful for many cases, right? So let's say you are walking near the Marina Bay, and you saw some accident, and you immediately tweeted that, right? And imagine that there is a model in the back end by the police department of this or the state defense department, and what they can do is they can automatically identify that this is a disaster tweet, and I can take the geolocation of where you are, and then I can take some reactive action, like I can go and look into that situation, right? So to give you an example, I'm not going to go through this because we don't have time, but if you at the end, let's say you give all these three sentences, like I met my friend by accident, and there is another sentence called Frank had a severe head injury after a car accident. So in both the cases we are using accident, right? But this is I met my friend by accident is not a disaster tweet, right? So let's see what that output looks like. Okay, don't worry about the model and all of that. We have not discussed today, but I just want to show you that since we are using BERT, and it is a model which contains the contextual information of every word in the sentence, it is not predicting this first sentence as a disastrous tweet just because it has the word accident, right? If you have used any traditional technique, it would have identified this as a disaster. But since we are using BERT, the BERT knows that here, although we have this word accident, but in this context, accident is not a disaster, right? Whereas in the second example, it has clearly a disaster, so it is predicting as a disaster. Now, we have not gone through what this SageMaker model and how we have trained this. Maybe I can have another session, but if you want to play around, feel free to look into this GitHub repo. I think we can share that. I'll paste that in the comment, or the team can send it to you, and we can go over this maybe in the next meetup. Okay, so that's about this session. But before we end up, if you have any questions, feel free to ask, or else I have a few simple questions, okay? And it has nothing to do with NLP. It's just for fun, so that we close our day with some learning around Python. Okay, so if you know the answer, I will just wait for 5 seconds and just type in your answer. So the question is, are booleans are actually integers in Python? Okay, so what do you feel? What should be, or in other words, what should be the output of this statement? Can anyone just ping on the chat? The question is a boolean are actually integers? Anyone? So let's say A is equal to true. Okay, so what is the type of true? It's bool, right? Now, is bool is int? So let's see this. Okay, it's true, right? So you are correct, Nitya, right? Okay, so feel free to ping me or at later point in time after this session. I'll share you AWS credits, as well as I'll share you one book. Okay, and I guess I missed that. So after this quiz, maybe I'll show it to you which book I'm going to share with all of you. Okay, and most of the content that I've presented, it's all from that book. It's a brilliant book. If you are seriously interested in Transformer, please feel free to read that book. Okay, so now the next question is this. Okay, so I'm giving you 20 seconds. Just tell me what M should print. Just read that carefully. What should be the output of M? Anyone? No one? What should be the what should this print statement return? Okay, try. Okay, okay, Anthony, you are absolutely correct. So it should return 1. That's correct. All right. Now this is to Anthony specially. Now you should tell me what should be the output of this. Anthony, what do you feel? Excellent. Right. So it's value by reference and value by current. So this is, I mean, I'm not, I know you all know this, but this is just for fun. Okay. Now, what should be, let's say A equal to 0.1 plus 0.1 plus 0.1 and B equal to 0.3. A equal to B. This should be quick, right? So I'll just wait for 5 seconds. What it should return? True? Okay, let's see this. It's false. Okay, so you can check this why it is false, but I'll give you an hint, and you can see that why this crazy behavior. Okay, and this is the last question of the day. So A equal to 10, B equal to 20. Okay. Now what should be the output of this? Yes, that's correct, Nitya. That's because of floating point truncation, right? So just check this question number 5. I'll just wait for 10 seconds. Can anyone type what should be the output of this particular statement? Okay. Anthony is saying 10, true, 20. Okay, let's see this. It's 10, false, 20, right? And it's correct, right? So because B is not equal to 10, because B we have defined it as 20, right? So that's about it, right? So, but initially when I looked at it, it's quite a weird statement. No one will use it in this way. So the idea of sharing all of this is these are few of the questions which were asked, not exactly the same way, but in some other way in various interviews, where I have attended in my past, and I could not able to answer any of those, right? So I just thought to, eat every one of your brain a little bit. All right. So with that, before I conclude, this is the book which I'm going to share it with you. I would strongly recommend that you can, have a physical copy, because I read physical copy. This is the book by Sudarshan. He's a great gentleman who writes books around deep learning and NLP, and it's a very recent book. So, and if you are into PyTorch, TensorFlow, you can refer to this, because this book is written in TensorFlow. I don't use TensorFlow that much, but this book is incredible, right? So feel free to use this, and everyone who responded in this chat, either you can ping me or the user group leader and share your email ID, or you can just ping me over LinkedIn. I'll share the book with you, and as well as I'll share the AWS credit so that you can play around this particular problem. Although I have not gone through this demo, but maybe we can go over this in the next meetup, and then you can make use of those credits at later point in time. So with that, I'll hand it over to the team. So let me just stop sharing. So back to you, Swarnima.
Yeah, thank you so much for the session today, Simon. Really, really appreciate it. And it'll be great to get into more around transformers and their architecture in a subsequent talk. So if you really enjoyed this, and it looks like the audience has, we'll be having a follow-up session hopefully sometime soon. Thank you all. There's also more credits to go around. So continue to attend data science talks. We'll be sharing more of those credits. And if you have any specific questions, please do reach out to Suman himself or to the Data Science SG organizers, myself, Kuping Chung, or Rizal, who is backstage today. Thank you all.
Sure. Thank you. Thanks, everyone.